All right, welcome to the last class. So the title of today is congratulations, because if you've made it to this point in the class, you're able to do machine learning at the level of someone in industry and able to go into a lot of exciting research projects, and you're probably highly marketable at this point if you took away all the details in this class. So congrats for making it this far. That's a big milestone. So a few announcements before we get started. We have this, oh, keep messing this up. Slideshow. Okay, yeah, so the course evaluations, please fill that out. This is my first time teaching this class. So it could help me design future iterations of the course. Just curious, who preferred the iPad notes portion? Okay. Who preferred the slides? Okay. Who thought it was appropriate based on what was? Okay, interesting. Okay, good to know. So yeah, just like things like that are like easy to change, just let me know. And yeah, I'm flexible with how I do it in the future. Machine learning is kind of the biggest topic in the world right now, or at least one of them. So it's important to get it right when teaching it. So any feedback would be amazing. And if we get above 95% class participation, then everyone gets +2 points. I don't want to do 100% because there's always that one person, but I feel like 95% is a reasonable threshold. I think right now we're at 60%. So keep them coming, and we're almost at 95%. And the other announcement, reminder of deadlines. So your final project code and write-up is due at midnight on May 9th on La Lima, and then the final exam is due May 15th at 5 p.m. Just because I need time to figure out everyone's grade by the May 16th noon deadline, and I don't want to miss it in the morning, or so just to give me time, 5 p.m. So right now I have 47 questions written. Who would prefer, oh, wait 1 second, and then I'll take questions. Who would prefer 50? So I think the midterm is 75 questions at 3 hours, right? So since I'm at 47, who would prefer 2 hours and 50 questions? Okay, who would prefer 3 hours, 75? Okay, that makes it easy for me. Most people said 2 hours and 50. But if y'all change your mind, just email me. Okay, sorry, any logistical questions? Yeah.
So the final due on May 15th? When is the final open for us to start?
No later than when the final project is due.
Okay.
So you'll at least have May 9th at midnight until May 15th, but possibly earlier. I just need to add 3 more questions and then like double check that. Yeah, I want to make sure there's nothing ambiguous, which I think it was mostly the case for the midterm. So just to double check. So it's May 2nd. Yeah, I should have it sooner than May 9th, but guaranteed by May 9th. Any other logistical questions? This is the last class. Okay. So the rough outline for today is we will start by talking about how ChatGPT works. We've already really talked about most of that. So just putting in the final pieces with reinforcement learning. And then I'll have a short advertisement on my lab's research on machine learning for healthcare, which is kind of a nice way to see some other types of things you could do with machine learning that we didn't get time to talk about in this class. And I'll just talk about opportunities to work with me. And it's kind of doubling as slightly new material or things beyond this class that you could learn about. We'll have a final exam review similar to the midterm review. I'll put a few multiple choice questions, and then we will briefly review the high level topics of this course, and we'll be done. So starting with ChatGPT. So the core ingredients of ChatGPT, which we all use, I'm sure, is first of all, it's based on an attention-based transformer decoder model, GPT. We talked about that previously. It's based on self-supervised pre-training or language modeling. We talked about that previously. And then the third component that we haven't really talked about is the reinforcement learning component, because we just learned about reinforcement learning. So now we can discuss that final component of ChatGPT. And the specific type of reinforcement learning used is called RLHF, or reinforcement learning from human feedback. So just to quickly review these first two components, this is not going to be too much detail because we spent the last few classes going at this, discussing this ad nauseum, but just a quick review. So the core neural network model that powers GPT is a transformer-based model called GPT. And the core ingredient of transformer-based models in general, whether it's the GPT variant or any other transformer-like model or attention-based model, is the idea of self-attention, which is highly technical, but at a conceptual level, it's looking at, for each input in an input sequence, how much should that input attend to other inputs in the sequence. So, for example, you could have the word "it," and it could be the animal at the beginning of the sentence, or it could be the street. I forget the language, what types of nouns those are, but you know what I mean, like whether it's the subject or the other one. Yeah, object. Thank you. And so we talked about the GPT model in particular, which is composed of several transformer blocks. The transformer blocks has multiple self-attention heads, which independently learn the self-attention weights, or how much to attend to. And that, coupled with just having a highly parameterized model or a neural network with a lot of weights to learn, makes it powerful enough to be used for things like language modeling. So that's the first key component, just having a giant neural network that has the ability to self-attend to the input sequence. And we talked about that a lot. The second core component is the idea of self-supervised learning, or self-supervised pre-training, which is really just, you could think of it as regular supervised learning, except the output is not generated by human labels, it's generated from the data itself. So an example of a self-supervised pre-training task that happens to be used to pre-train GPT is forecasting words. So you can get all the text on the internet and predict what's the next word. And if you do that, you don't need any human labels, you just need to get the text. And that's what enabled GPT and OpenAI to just download all of Wikipedia and download all the text on the internet and train the model accordingly. And so kind of a simple idea, but when done at scale, it's been incredibly powerful and led to state-of-the-art performance. And so in particular, this is what it looks like. You have the beginning of the sentence as the input, and you go through the GPT model and you predict the next few words. And when training that, you don't need any human labels. And if you can do that successfully, then you have a model that understands a lot about how human language works, because it's able to predict what the next word should be for any given text. And so if you can do that, then your weights are pretty close to the space and the parameter space that's vast in this case that would give you an optimal language model. Think of it in terms of the gradient descent visualization. Okay, so the third ingredient, adding in this reinforcement learning topic we recently learned about, is reinforcement learning from human feedback. The general idea is that the OpenAI has trained a reward model, so a neural network that predicts the reward of a response to a prompt. And then they use that model to optimize a policy model, which is another neural network, using a variation of policy-based reinforcement learning. And that policy model's job is to generate text. So you have a GPT-based policy neural network that generates the text, that's the policy, and that policy is updated through the reward that's observed through this reward model. So you might be asking, well, why do we need reinforcement learning for this? Why can't we just train it to predict responses to prompts that are good? I think the thinking that OpenAI had for this is that conversations are this dynamic, time-based process. And so your responses to a given prompt could be based on previous responses and previous prompts by the user. It's a conversation. And so based on where you are in the conversation, you're at a different state. And so your response is going to be different depending on where you are in the conversation, or at least that's the intuition behind using reinforcement learning rather than like regular supervised learning. So at a high level, just on a pictorial level, you have your policy network, a text generator, GPT model that generates text. And then the reward network takes that generated text and outputs a reward, which is used to update the policy using all the reinforcement learning stuff we talked about last class. Now, in particular, OpenAI has used a variant of reinforcement learning we haven't talked about called proximal policy optimization. It's a model-free policy estimation method. So we know what model-free means from last class. We know what policy estimation is. So it's one way of doing that. I don't think using PPO is particularly, like PPO itself is the key to what makes ChatGPT work. I think that OpenAI happened to use PPO with a large data set, and it worked well because they had a large data set. Other companies like Google have used other reinforcement learning paradigms that are not PPO, and it's also done well. So we don't need to go into the details of PPO specifically because it's really just the idea of using reinforcement learning. OpenAI happened to use PPO. They happened to use a GPT transformer model, but probably this would have worked just as well with a different type of reinforcement learning, different type of transformer model or attention-based model. We don't know because it takes a lot of computing power, but that's my hunch. I don't think they had any proofs showing that that's the best method to use. That's just what they happen to use. I know in Google's case, they had the infrastructure built in their company for a different policy, different type of reinforcement learning paradigm. So that's why they went with that. It was just easier to use that based on their existing code. Yeah, so it's a lot of this theoretical stuff. It's not always the reason for decisions in the real world. Sometimes it's based on convenience. And if it works just as well, then great. So going into the steps with a little bit more detail, and this is about all the level of detail I'll go in. So the first step is to just using regular supervised learning to fine-tune the policy model or the text generator. So you start with GPT that's been pre-trained using self-supervised learning on all the text, right? So it starts off by predicting what's the next word using all the text on the internet that it can get. And that's your starting point going into step one. You already have that model. And so starting from that, you have a data set of prompts with answers. And GPT has gotten a lot of human labelers to give answers to prompts. And so they just start with that. They hire a bunch of people to provide answers to prompts, and that using regular supervised fine-tuning, they fine-tune their pre-trained GPT model using regular supervised learning to answer those prompts. And that's their starting policy going into the reinforcement learning. Good so far in step one? Okay, so that's the starting point. Then step two is separately to train the reward model. So there's two models interacting with each other. We have the policy text generator trained. Next step is to train the separate reward model. So the way they train the reward model is they, again, have a lot of prompts and a lot of labelers that they hire, and they have multiple labelers. They have multiple labelers and multiple responses to each prompt. And what they do is they ask the human labelers to rank the prompts and the answers to the prompts. And so if you have answer A, B, C, and D, you could say that answer D is better than answer C, which is better than answer A, which is better than answer B. That's what these human labelers are tasked with doing. And then they train the reward model using a loss function that basically looks at comparative betterness of the responses. Okay, so then you have your reward model. And then finally, step 3 is to do the reinforcement learning. So you have your policy network trained, you have your reward network trained, and then you sample a new prompt from your data set of prompts. Or ChatGPT, or sorry, OpenAI takes, answers the prompt using the policy network, feeds the answer into the reward model. The reward model then is used to update the policy using reinforcement learning. So that's how ChatGPT was trained. And all these components, like there's no part of how ChatGPT is trained that you don't know about at this point. So any questions? That's about it. We did most of the hard work for how ChatGPT works in the past several classes. So putting it all together is kind of an easy task given where we've gotten to. So now you know how that works, which is pretty cool. I'm sure next year there'll be some new other hot AI thing that will be the focus of the last few lectures. But right now, and I'm sure it'll just be some other creative combination of the topics we learned about in class. That's just how it goes. So hopefully y'all will go out and creatively combine the topics, the building blocks that we've learned about in class to create something like ChatGPT, although you need a lot of computing power. So maybe work for a company that does that. Although Mana could be kind of cool. Anyways, I had some students who are like, let's build a foundation model, which is like, let's just do this pre-training on a large data set and just release that. I was like, that's a good idea. Yeah, let's just have a model that's continuously learning to predict, not the next word, but the equivalent of that for other types of data. Kind of a cool research project if anyone wants to do that. Okay, so we now know the core ingredients of ChatGPT. I asked ChatGPT, what types of real-world projects can someone who completed a machine learning class now accomplish? And ChatGPT said image classification, and gave a lot of examples: natural language processing, fraud detection, predictive maintenance, kind of random recommendation system, time series analysis, kind of but it goes into examples. So within time series analysis, finance, weather forecasting, traffic prediction, within recommender systems, e-commerce site or music streaming service, within predictive maintenance, manufacturing, transportation, energy, etc. So you could use everything we learn in whatever industry you want to go into. I also asked, what kind of jobs can someone who knows Python, scikit-learn, TensorFlow, and the basics of machine learning theory get? Can someone get who knows those? What are the typical salaries? So you can just look and see, like, probably after this class, this is the rough starting salary you can expect. So that's good. So hopefully you'll go out and get those jobs, which there are so many of right now because every company wants machine learning engineers. So like, even if you're not in computer science, just go and get paid. I mean, you don't have to, but you can if you want to. So that's a good place to be at as a result of this class. Okay, so now I want to talk about my research, and I will put a timer on myself for 15 minutes just to be sure that I don't go on for too long, because we also want to do the final exam review, which I'm sure is the reason why all of you are here. Starting now. Okay, but so, I teach and all that, but like technically a professor's primary job is in principle to lead a research lab. And so my research lab is the Hawaii Digital Healthcare Lab, where we do a bunch of computer science research for healthcare, including machine learning, not just machine learning, but machine learning is a big part of that. So today I'm just going to talk about the subset of my research, which is machine learning. But I will say, I also if you do web development or mobile development, I also have a lot of projects there if you're interested. Not going to talk about that here because this is a machine learning class. But yeah, I am taking a lot of students. So roughly what a big part of my lab does is digital phenotyping, which is the idea of using digital devices that we all have already, like our smartphones and our laptops and social media and things like that, to provide healthcare for behavioral and psychiatric health conditions. Wearables, Fitbits, Apple Watch, Google Glass, although not really anymore, but the equivalent, augmented reality, and collect data from those devices that can be fed into a machine learning model to predict that someone's health outcomes, or to provide a diagnosis, or to screen for a condition, or to create a adaptive digital therapy that is not one size fits all. So like you can imagine a mental health app. Imagine if you had a mental health app that was just the same thing no matter who used it. You could see how that might go badly. You could imagine like that's actually a really bad idea. So you use machine learning to personalize that experience to the user, things like that. So I'm just going to talk about some of the interesting machine learning tasks that I work on that are required to solve a lot of these health issues. One of them is multimodal machine learning. That's something we didn't talk about in this class, but the basic idea is that you can take multiple types of inputs together and use those to make a prediction. So for example, in this IoT wearable world, you can get all the different sensors on your wearable watch, all the different sensors on your phone, have different signals, time series signals, and use each of those as separate inputs into a single machine learning model. So we've done this for a bunch of different tasks. Another one is fair machine learning, which we have Armin actually who's in this class is working towards. So the idea of fair machine, and other students as well, just not in this class or not here today at least. So fair machine learning is the idea that if you train a machine learning model with different amounts of data from different groups, for example, different demographic groups, then what tends to happen is the machine learning model tends to perform differently and usually worse for the underrepresented groups in the training data. So are there algorithmic ways to handle that? And so one way is regularization. So remember, beginning of this class, and it might show up on the final, regularization, where you add a penalty or add a term to your loss function for undesirable properties. In the case of L1 and L2 regularization, which you learned about, that undesirable property was having too many model weights or having model weights that are too big, but you can penalize your model for other things too. So in this case, if you can quantitatively define bias or fairness, which there are many quantitative definitions of, and you can imagine how would you define fairness mathematically, but there's many ways to do it. And based on that, you add that type of regularization to the loss function. So you're optimizing to jointly minimize error and maximize fairness, or minimize bias. So minimize error and bias, basically. So that's one approach. Another approach is upsampling through data augmentation, ideally generative data augmentation, so like GANs and stuff. It's a little hard to do, but there are research labs out there, that's not my lab, that like have dedicated their entire research career to fair machine learning with generative models. So like that could be a theme of an entire research lab, and it is in some other schools. So I'm gonna start looking at that too, just because it's useful for healthcare research, and it's very important for health, like diagnostic models, to work equally for different groups. It shouldn't work preferably for some groups versus others. Another area I work in is personalized machine learning. So in this class, we've been talking all about how we want a single machine learning model that works for everyone. And I think that in healthcare, sometimes we have situations where you have repeated health outcomes you want to measure, like stress or like blood glucose levels being too high, or things like that that are kind of high blood pressure, repeated events within a person. And instead of training a general model that's going to predict these complex, often subjective things like stress for everyone, train a separate model per person and totally overfit to that person, but overfit in a good way because the model's only going to be used on that person. But then to support that, can we do self-supervised pre-training like we just learned about and like ChatGPT does to learn the baseline dynamics of that person's, for example, Fitbit biosignals, and allow people to basically provide a few labels of a complicated subjective thing like stress and have the self-supervised learning learn all the details about how their body works and then be able to fine-tune just a few labels to these complex tasks. And that's been shown to work surprisingly well. And so we're working on publishing a few papers on that note. And you can imagine different self-supervised ways of pre-training these signals models. So really excited to get that publication out, but there's a lot more to do there in personalized machine learning. So that's another one. And yeah, good results. I'm also in the business of creating benchmark data sets. So you might have found through your final projects that a lot of the data sets are, there's limited in what you can do. I mean, like there's some data sets in some areas that are really popular, but let's say you want to do a project and there's no data set for it. Well, then you're kind of lost. And also what tends to happen, as you might have seen, is when people post a data set and make it publicly available, then all sorts of people for the final projects in their classes at various schools or in research labs trying to make a new machine learning model and wanting to test it on a particular data set, they use your data set. And so by kind of releasing a new benchmark data set with certain properties, but specific to health conditions that don't exist public data sets for, we could sort of crowdsource to machine learning and people and data science people the task of creating machine learning models that work really well just by releasing the data set and putting it on Kaggle or UCI machine learning repository. So a lot of what projects I'm working on are in the business of creating these data sets, maybe making a first pass towards predicting with them, but then releasing it to the world and letting everyone build better models, which is, in my opinion, a great thing. Like people who are, experts, I mean, even more experts at machine learning can handle it. And yeah, so yeah, it's exciting. We've done this for Twitter data, and we're doing it for meth data. I guess I should give more context there. So we have a partnership. Actually, I'll go into it in the applications part. So yes, question.
So with benchmark data sets, especially for healthcare, and I apologize, you already said it. What are the, maybe not ethical dilemmas, but like privacy? Like, how do you ensure when you're adding data in, it can't be traced back to a certain patient? Or is it you collect data from patients who have given their authorization? And I guess just if you could touch on just kind of that, how you would build something like that to kind of help ease over some of these ethical things that might pop up if someone wanted to say use this data set or even in its development.
Yeah. I mean, so great questions. The question was, how do you handle the ethical issues? And so there's two types of studies. I mean, I have many studies. A lot of the studies, it's, we get people to sign a consent form and they're fully aware. The other side of things are like scraping things from the internet. In those studies, it's only on already publicly available data. And it's kind of become the standard in machine, like ImageNet is scraped from the internet. Some of the most popular data sets are scraped from the internet. And everyone uses ImageNet, right? So it's kind of common practice to do that. I think there should be a lot of ethical debates and figuring all that stuff out. And we talk about that extensively in my human-centered AI and data science classes. So you should definitely take that if you're interested in that kind of stuff. But yeah, it's TBD, but just to say that like things like ImageNet, it's already kind of the standard status quo to scrape from the internet and crowdsource the labels and release that publicly. Yeah. Yes. Yeah. So federated learning is the idea. So the question was about federated learning. Federated learning is another cool thing, type of machine learning where you train models locally and you only update the weights to a central server. And so only the people who have the data have their models, and they upload just the M's and the B's of the MX plus B or the thetas. And then you combine all of those to make a central model. So you're never sharing data with a central authority, you're sharing model weights. It's kind of a cool area that some of my collaborators are looking at. And so yeah, I do explore that as well, and am looking at doing that more if anyone's interested in federated learning. Yeah, great questions. Yeah, these are also questions, by the way, even though it's not machine learning research. A lot of my research is more on the human computer interaction side of things. So if you're interested in exploring these ethical issues and writing a paper about that, and like interviewing people and seeing what they want, and really doing this human-centered, qualitative, but centered in machine learning topics type of research is kind of cool. I totally do that too. So talk to me if you're interested in that. And that's very publishable and a very hot topic. Okay, so I do look at a lot of applications. So one that I've in partnership with JabSum, with Kiave. Does anyone know about the hula study here? Well, basically they showed that hula dancing reduces blood pressure by a lot. So I'm trying to use wearable devices to detect when people might have stress-induced hypertension, and then provide a digital intervention that can detect when people are doing something in a non-invasive way that would indicate that they're going to have stress-induced hypertension, and using the personalized machine learning, and then intervening using an app, basically. So there's that. I have to go quick because I only have 2 minutes left. So just quick whirlwind tour of the application. So I've gotten funding for a big project in partnership with Kaiser Permanente and the Hawaii Health and Harm Reduction Center and the Department of Psychiatry at JabSum and Queens to, I didn't put Queens on here. Anyways, with Queens to measure, do this personalized machine learning method for detecting meth cravings and meth use, again, using wearables and using the personalized machine learning. There's no way you can build a generalized machine learning model to do that. That's crazy. But with personalized machine learning, where you're totally overfit to the person, you can do it. By the way, think of like Face ID as the analogy. That's the type of thing I'm talking about. Social media data mining. So how can we create data sets or analyze things from social media? It's a big research field in biomedical data science. So there's a lot of researchers doing this. For example, for analysis of autism screening, nicotine. So in partnership with UH Cancer Center, and some professors there, predicting who's a cigarette user or not based on their tweet. NIH, National Institute of Health, and CDC are very, very interested in this type of public health surveillance from social media data. So those projects, I partnered with the Hawaii Parkinson's Foundation and the leader of that association to detect Parkinson's from playing games on a computer. So basically using, one of the symptoms of Parkinson's is hand tremor. So basically, can you use keyboard presses and mouse movements in the context of a structured game to diagnose Parkinson's? A lot of people have done this already, and we're collecting data. Personalized mood analysis, take a selfie and predict your mood, again, using personalized machine learning, totally not possible without the personalized part. Classification of dementia using natural language processing. Oh, yes, I can't say much more. Cancer diagnostics and screening. This is a big one, but I can't talk about it. Digital autism diagnostics in partnership with Stanford, another big one, but I can't talk about it. Pediatric sleep behavior analysis in partnership with Baylor College of Medicine, another big one, but I can't talk about it. Machine learning on NIH data sets. There's this Alvis research project, but I can't talk about it. There's Hawaii specific data projects, multi-ethnic cohort study, and then the HIP EMR breast cancer data. I can't talk about it. So all I could say is that there's a lot of projects that I'm working on, and there's many opportunities to work with me. For if you're an undergraduate student, A lot of undergrads don't know that you could take ICS 499 and like have that count as an easy A course. I mean, like a completion type of course, and you get credits for doing research for a semester, and it totally counts as an elective. That's the question.
What is ICS 499?
It's the research project or creative work thing. I don't know. It's like the project with a professor for class credit one. And so you would sign up with a specific professor. I take a lot of students on that. Again, usually, unless you don't do anything, it's an easy A. There's this another thing undergrad students don't know about is the undergraduate research OP, whatever that stands for, program, which basically pays undergrads, college students to do research for a semester. If you're further along in your career, like probably you are if you're in this class, it's about 5,000 per semester. It can double as your honors thesis. I have some students who are doing all three of these, like getting them early and doing all three of these things throughout their career. So you could do your honors thesis with me. I basically have no cap on these things. So whoever wants to do it, I'm happy to take you on, unless you like never do work, but otherwise let's do it. Graduate students, I'm happy to so same thing, you get course credits, ICS 699 and or 700. Course credits, usually it counts towards a degree, especially Plan A degree. So if you want to do a master's thesis, I can mentor you for that. Only caveat is usually that I have to have a big say in what the project is. But if you like don't know what you want to do, but it's you want to do something in machine learning for healthcare, or again, not like human computer interaction for healthcare, or web development or mobile development for healthcare, or like running research studies and working with people directly, any of those things. But because this is a machine learning class, machine learning for healthcare, you can take those credits with me. And if it all goes well, I can be your PhD advisor. I tend to work with students, working with students in this capacity for at least a year before making a decision about whether I'd be your PhD advisor. But if you're an undergrad and we do that, then it might, you might directly start your grad school experience with me as your PhD advisor if it goes well. If all goes well, there's a big possibility of RA and GA ships. So like if you're funding your grad school through TA ships and you'd rather just do research instead, you could do that. There's limited spots, and there's this big grant that's likely to come through in this summer, but it's TBD. But if that happens, there will be a lot of open positions. So just keep that in mind, but I won't know for sure until end of this summer. So yeah, those are opportunities to work with me. Hope y'all, or some of y'all, choose to. And I hope just seeing all these things that I work on shows you how you can take what we've learned in this class, apply it to the real world, and kind of build new methods that are required to solve healthcare problems: multimodal, fairness, personalization, and then like putting it into applications that actually help people for healthcare. But you can do all those things outside of healthcare as well. Yes.
Writing an honors thesis as an undergraduate student, that's also just like another research opportunity.
Yeah, I don't know the detail. I know that some students have come to me talking about honors thesis. I don't know the details of that, but I'm curious to know if anyone knows. Yeah, sorry, I don't know the details, but if I know it exists, so if you know the details, I'm happy to mentor you through that. Okay, so just contact me if you're interested. There is a plethora of projects. Okay, so now the reason that you're all actually here is the final exam review. So similar to previously, we'll have a few practice questions. So we'll start off with, which of the following algorithms is used for unsupervised learning? Who thinks A? Who thinks B? Who thinks C? Who thinks D? Cool. So there will be like questions prior to all this deep learning stuff on the final, and some that kind of combine it all into one question. So which of the following best describes self-attention in the context of deep learning? Let me give you a few, and remember it's all open notes, but let me give you a few seconds to read over it. Who thinks it's A? Okay, seems like a lot of people. Who thinks B? Who thinks C? Yeah, so like, again, like you'd have to know all the details like query key value. If you're paying attention just broadly in this class, it should be a pretty easy final. Which of the following best describes the role of Q networks in deep Q learning? Do a few seconds. Okay, who thinks it's A? Who thinks it's B? Who thinks it's C? Okay, so most people abstained, but some people did say B, and those who said it are correct. Just the definition of a Q network, it's the value of the state action pair, just kind of by definition. But you can look it up if you're don't memorize it, which you don't need to. Okay, which of the following trade-offs between, oh, also all the questions on homework 5 are other questions. So these are like additional questions. And all of these and combined with the homework question should give you an idea of the types of questions you'll get. Okay, which of the following trade-offs between types of neural network architectures is true? A lot of text, so I'll give you a few seconds while you're reading. Also, all the midterm types of questions are fair game as well. I'm just not emphasizing those here because you already did that. Okay, who thinks it's A? Who thinks it's B? Who thinks it's C? Who thinks it's D? Okay, most people said C, and that is correct. Okay, suppose you are training a neural network for a classification task with a large data set. During training, you notice that the model is overfitting to the training data as the training accuracy is much higher than the validation accuracy. Which of the following is a potential solution to reduce overfitting? So I guess you could have just had that last sentence. Oh well. Who thinks it's A? Who thinks it's B? Who thinks it's C? Who thinks it's D? Okay, cool. Oh, you're gonna do great on the final, I can tell. Suppose you are training a deep neural network on a large data set. After several training epochs, you notice that the network's training loss continues to decrease, but the validation loss plateaus and then starts to increase. Which of the following is a possible explanation for this behavior? Okay, who thinks it's A? Who thinks it's B? Who thinks it's C? Okay, so most people said B. What is correct? Again, it's loss, not accuracy or F1 score or anything. So loss you want to be lower. Okay, I just put the answer here because there was a question like that on the homework. But the point is like all the homework types of questions are fair game. All the midterm types of questions are fair game. And there will be some questions like here, I only showed things that compared neural network architectures, but there's some questions that compare between the neural networks and the more classical models all in one question. So you might get that type of question as well. Yeah.
Calculate the size of things or of outputs after
Yeah. Let me stop sharing and remove my blurred background. So the question was walk through how the so basically that question, like how would we answer this question? Okay. Okay, let me stop sharing. Yeah, so let's say in this case we have a 1000 by 1000 by 3 input image, and so basically we have that is our input image with dimensions 1000 pixels by 1000 pixels by RGB. And we apply convolutional layer with 50 5 by 5. I guess it's implied by 3 kernels. Actually, no, never mind. 5 by 5 kernels, so 5 by 5. So the question is, what would the size of the output tensor be? So we do that dot product across the input image, the dot product of the vector version of the matrix. If that wasn't clear. And so we get a single number for here, then we slide it, and then we get a single number for here, and we slide it. Because it says stride is 2 and no padding, that means that we skip 2 each time. And I think the easiest way to think about the question is actually, maybe you think about it differently, but just look at a small example. Like what would happen if you had a 8 by 8, or sorry, let's do 9 by 9, and we had a 5 by 5, and then we moved, we get a single output number here, we move by 2 because stride is 2. So now we're at index 2 through 7, that gives us another number, and then we move by 2, we're at index 4 through 9, that gives us a third number. And the same thing will happen this way. So we know that when the input dimension is 9 by 9, we get the output is reduced by like dividing it by 2 essentially, and then subtracting and then rounding off. So maybe it's hard. Sorry, let me do a even number because that might be an easier example. So if it's 10 by 10, we can have 5 by 5, move over 2 to 7, move over 4 to 9, move over, and no padding. Yeah, actually, I realize this question's no good, so I'm just gonna delete it. Let me go to the homework question, because that'll make it much more easier to explain.
So the result is how much we cover in those
Yeah.
slides of 2?
Yeah, let me go to the homework question. So 1000 by 1000 by 3, like we have in the homework. Yeah, that'll be a better one. The stride equals 2. You could get that type of variation, but it's actually, I wouldn't put that on the exam because it would be a little difficult to calculate. So in the place of the homework though, okay, so you have 50 5 by 5 kernels, and you just have the stride equals 1 and no padding. Okay, so if you do this, you move by 1 each time. So okay, so if we think about the smaller example, let's say 8 by 8, we have 1 through 5, 2 through 6. So 1 through 5, we shift it over, do the dot product, 2 through 6, shift it over, 3 through 7, shift it over, 4 through 8. And so if we do that for every row, we end up with a 4 by 4 output. So we see that when we have 8 by 8, that actually gives us 4 minus a 4. The output dimension is 4 units smaller. So we can look at that for a bigger example. Let's say if we go to 10 by 10 and do the same thing. So 5 by 5, 1 through 5, that gives us an output. 2 through 6, that gives us an output. 3 through 7, that gives us an output. 4 through 8, that gives us an output. 5 through 9, that gives us an output, and 6 through 10. And we do that for each row. So if we work it out in that example, we see that again, it ends up with a 6 by 6 output, which is 4 smaller than the input. So we start to see that the pattern is that the output dimension is just 4 smaller than the input, just by working out a few examples. And so you can generalize that to 1,000. I mean, this is how I think about it. There's many other ways to think about it. So then, okay, you know that's going to be 4 smaller than 1,000, 4 smaller than 1,000, and the by 3 doesn't or sorry, and then we have 50 kernels, so then we have 50 output dimensions. So then the by 50 part is kind of easy because we know that we have 50 kernels, so obviously that's going to be the last dimension. And then you're just working out, is it 5 smaller when you slide it over, or is it 4 smaller when you slide it over? And again, working it out on a few smaller examples, it kind of makes it easier to think about in the large example. Does that help? Yeah.
So if you had a kernel that was say like 6 by 6, would it be 5 smaller?
So 6 by 6 would be, you just think about it. So you'd have 5 by 5. That gives you an output, slide it over. 5 by 5, that gives you an output, slide it down. 5 by 5, that gives you an output, slide it to the right. 5 by 5, so it'd be 2 by 2, and that's 4 small.
If the kernel was 6 by 6, would the
Oh.
output be 5 smaller? So is it always like it's 4 smaller because it was a 5 by 5 kernel, so it'd be 5 smaller if it's a 6 by 6 kernel? So
Yeah, I believe so, and you can just work it out and see if that's the case. I mean, it's just like how much room is there to slide. That's the extent to the mathematical nature of it. Like how much can you slide if you're sliding in a matrix? In a very informal way of saying it. Does that make sense to people? Did everyone get that right on the homework? Okay, cool. I guess you wouldn't raise your hand if you did. And then you could do a cost benefit of, is it worth turning it in late, a day late, to now that you know that answer. Anyways. Okay, so that's that. So the very last topic is just a summary. So the core ingredients of machine learning that we've talked about throughout this whole class, that are really independent of any of the methods we've learned, that are kind of in all of at least supervised machine learning, is first step, how do you represent your input data or features? There's many ways to do that. We talked about what are you trying to optimize for? Or in other words, what is your loss function? What type of model are you going to use? We learned about many models, and how will you evaluate your model for success? So going into each of these, in feature representations, one of the core ingredients, we talked about several things you can do, and that was largely the focus of the coding part of homework 4. You can reduce the dimensionality of the input. You can engineer a creative representation. So with dimensionality, like PCA or autoencoders, but there's many other methods as well. Tisney is a popular one. There's feature representation engineering. So we talked early on about words, using bag of words, and then word to vec early on in the coding notebooks. And then we saw with image processing, you can define kernels that allow you to extract specific features. And for the longest time, people from images, and for the longest time, people hand engineered those. But then with CNNs, they were automatically learned. But there's many other ways, like with self-supervised learning, you could learn good features, as well as feature selection. So we talked about a few different ways you can figure out which inputs of the model to throw away to prevent overfitting. Then moving on to what are we trying to optimize? Well, that's our loss function. What are we trying to get the model to learn? The very first one we talked about was mean squared error for regression, which conveniently turns out to be how you evaluate that model as well, usually, or at least some variant of it. Root mean squared error or mean absolute error, you could use any of them. For classification, cross entropy loss, which we derived for logistic regression early on this semester, and is also used in neural networks. So for mean squared error and cross entropy, those are also the loss functions for neural networks. So again, linear and logistic regression are just a really small neural network with just an input and output layer, no hidden layers. So you could just generalize that to a deep network by adding hidden layers. And then we talked about later in the class, all these custom loss functions for cool new creative applications. So reinforcement learning had different loss functions. Different types of generative models had their own loss functions. The self-supervised representation learning, like in the chat, like GPT, pre-training the forecasting, that has its own loss function often. So you have to define what you're trying to optimize. And then you can add regularization. What do you penalize? Yes, you might want to minimize error, but you might also want to minimize other undesirable things like bias or having too many model weights. And that's where regularization comes in. We talked about a bunch of types of models. The first 2.5 months or so, or 3 months of this class was on classical machine learning models that work well with simple data, so tabular data, CSV files. If you ever have data in an Excel spreadsheet, you probably want to use those models. But then when you have complex data like images, video, text, sound, etc., then that's where deep learning tends to perform really well. And so we've learned about all types of models in both of these categories. And then finally, once you've built a model, you've chosen a model, you've represented how the inputs will look, and you've represented how you're trying to optimize the output to be, you got to evaluate how well does it do. And so we talked about various regression and classification evaluation metrics early in the semester. And then we talked about specialized evaluation metrics for all these special applications we learned about in the end. All this is to say that ML is largely an art as well as a science. There's, things like ChatGPT. That's one way you could build it, but you could also probably build it just as successfully with all sorts of variations on the reinforcement learning, on the specific loss functions, on the hyperparameters, on the input data going in, et cetera, et cetera. There's many applications to machine learning. There's this list which is generated every year. That's some of the 100 exciting startup companies that are using machine learning. So I've talked a lot about the big companies like OpenAI and Google, but you can see that machine learning is used in all sorts of fields. And because there's actually a small list that's cut out a lot of companies because it's only limited to 100. It's the top 100 out of many more than 100. But you see that there's companies in healthcare, finance and insurance, transportation, construction, media and entertainment, government, food and agriculture, retail, cybersecurity, business sales, developer tools, mining, apparently. So yeah, all sorts of things you can do with machine learning. So I'll leave you with this. Go out and change the world. Use machine learning in whatever you're passionate about. And congratulations for completing the class. Have a great summer. Thanks.